Most of us look up at the night sky and assume we missed the window. We dream about humanity spreading across the galaxy, but accept that we were born too early to actually see it happen. But the math says otherwise. According to current estimates from both NASA and the private sector, we already have the engineering and the physical technology to start building a permanent base on the moon right now. The price tag to get this done is between $20 and $40 billion, spread out over about 10 years. This is the International Space Station. To put that $40 billion number in perspective, this orbital facility cost roughly the same amount. It is also comparable to the budget surplus Germany had in a single year, 2017. For what amounts to a rounding error in global government spending, the moon offers us an immediate, accessible sandbox to test new technologies and tap into a practically limitless supply of raw materials. Taking another world requires a specific process. Throughout history, colonization has reliably followed three distinct steps: brief exploration, dependent outposts, and finally, permanent settlement. Phase 1 is the scouting mission. Governments or wealthy monarchs fund expeditions simply to map the terrain, plant a flag, and leave. We checked that box 60 years ago when the Apollo missions put the first boots and the first flags into the lunar dust. Since then, orbital satellites and robotic rovers have completely finished the job. They have mapped the craters and identified exactly where crucial deposits of ice and metal are hiding. The data is in our hands. The scouting phase is definitively over. The only thing standing between us and Phase 2 is the decision to actually go. Escaping Earth's gravity with heavy materials is incredibly expensive. To establish a Phase 2 outpost, our initial shipments have to be as light as possible, and they have to withstand a brutal environment. A lunar day lasts nearly a month, with temperature swings of 300 degrees Celsius between the baking sun and the freezing shade. There is no atmosphere to block cosmic radiation or high-speed micrometeorites. The most efficient solution is to send deflated, lightweight modules. Once they land, they expand into pressurized habitats designed to keep a rotating crew of about a dozen scientists and engineers alive. To shield these fragile modules from the deadly surface conditions, we have to tuck them into natural geological shelters, like the constant shadows of polar craters or deep underground inside ancient, hollowed-out lava tubes. But this is still just a foothold. These crews rely entirely on supply drops from home. If Earth stops sending rockets, the habitats will lose power and be abandoned to the dark. To survive long-term, the outpost has to use what is already there. The crew's immediate priority will be locating, extracting, and purifying lunar ice. At first, that water serves basic survival needs. It provides drinking supplies, hydrates experimental indoor crops, and charges hydrogen fuel cells to keep the base running through the weeks of freezing lunar night. Water is chemically split into hydrogen and oxygen, refined, and launched to an orbiting depot as rocket fuel. Since lifting fuel in low lunar gravity takes little energy, spacecraft arriving from Earth can dock, fill up, and continue their journey to Mars. Solving the logistical hurdle of deep space refueling transforms the moon into a necessary gateway for every mission heading to Mars and the outer solar system. To prevent the base from being abandoned, it has to cross the threshold into Phase 3. It must become a self-sufficient colony that pays for its own existence by generating wealth through commercial exports to Earth. This is when private mining contractors arrive. They will target the rich deposits of precious metals scattered across impact craters and sift the lunar dust for an extremely rare isotope called helium-3. Helium-3 is an isotope that scientists are currently researching for use in nuclear fusion reactors. If we can master commercial fusion technology, lunar helium-3 would provide the necessary fuel to generate clean energy for Earth. Scaling up that extraction requires heavy infrastructure. Instead of shipping steel from Earth, robotic mining rigs will begin churning that dark lunar dust, extracting the raw ingredients to 3D print massive concrete structures directly onto the surface. Heavy, autonomous industry will eventually replace small-scale scientific experiments, allowing the settlement's physical footprint to expand at an accelerating rate. The seed of a colony finally and irreversibly takes root with the birth of the first extraterrestrial child. A growing, permanent population, means the colony can no longer afford to waste a single molecule. Engineers will be forced to perfect closed-loop survival systems, building crops that need minimal water, perfectly efficient carbon dioxide scrubbers, and networks that reuse absolutely everything. Eventually, they will build a space elevator, a physical tether stretching from the lunar surface up into orbit, ferrying raw materials and people back and forth, without requiring a single explosive rocket launch. This level of independence creates immediate political tension. Existing treaties stating that no nation can own the moon will be rewritten. Will the first lunar generation adopt the national identities of their parents, or will they eventually decide to sever ties and govern themselves? However those borders are drawn, a self-sustaining base on the moon provides us with the blueprint for expanding across the solar system. More importantly, it gives humanity a permanent, functioning backup drive in the dark.